Hello, welcome to the fourth part of week 8 of the ECE9013 course. In this part, we will be showing examples of three complexity classes, which are the logarithmic class, the log-linear class, and the polynomial class. So, starting off with the logarithmic complexity class, as the name suggests, this group of algorithms have a complexity that grows as the log of the size of one of its inputs. Two examples of such algorithms is the bisection search algorithm and the binary search of a list. Starting with the binary search algorithm, suppose we want to know if a particular element is present in a list. The linear search method that we previously presented just walks down the list, checking each element. So in that case, the complexity was linear in the length of the list. Suppose we know that the list is ordered from smallest to largest. How can this knowledge help us provide a more efficient search mechanism? The binary search method works as follows. We pick an index I that divides the lists into two equal halves. We check if the list I element at index I is equal to the element that we're searching for. If not, we check if that element is larger or smaller than E. Depending on the answer, we either search left or right half of the list. This somehow is a new version of a divide and conquer algorithm. We basically break the problem into smaller versions with smaller lists plus some simple operations. And the answer to the smaller version is an answer to the original problem. So in this case, we start with the whole list. We find the element at the midpoint of the list and check if it's greater or less than the element that we're searching for. And depending on that, for example, in this case, we are searching in the left-hand side of the list. This one has n over 2 elements. In the following iteration, it will be n over 4, and so on. So if we finish looking through all of the lists, we can do it in n over 2 to the power I, because in every iteration, the list size is divided by 2. So in this case, the complexity of the recursion is in the order of log of n, where n is the length of the list. Now, moving to the bisection search algorithm, we show two different implementations. In the first one, we check first whether the list is empty or if the length of the list is 1, that is, it only contains one element. These operations are of order 1 because it's a simple checking operation. Else, we would divide the length of the list by half and then recursively call the same algorithm again. So here, this is not a constant because here we are taking another copy of the list to search within it. So with this implementation, we have all log n bisection search calls. In each recursive call, the size is cut by half. So if the original size is n, then the iterative calls or recursive calls will be in the order of log of n. We also need order of n for each bisection search call to copy the list, because in this part we are actually making another copy of the list. This is the cost to set up each call, so we do this for every level of recursion. If we are really careful, we can note that the length of the list to be copied is also halved on each recursive call. Turns out that the total cost to copy is order n, and this dominates the log n cost due to the recursive calls. So we still reduce the size of the problem by a factor of 2 on each step, but we need to keep track of the low and high portion of the list to be searched and avoid copying the list. So this is another alternative for the bisection search algorithm. And in this case, again, the order would be log n. So this is the implementation of the alternative, in which we only need to keep track of the higher limit and lower limit of the range and perform the recursive call basically once. So in this case, because we don't need to make a copy of the list again, the order is of log n rather than n log n as shown for the first implementation of the bisection algorithm. This is another example for the logarithmic complexity, and here we are determining the number of times that we can divide the digit by 10. So we only have to look at the loop since there are no function calls. Within the while loop, there's a constant number of steps. So how many times do we go through the loop? That is, how many times can one divide I by 10? So this again is of order log I, because in every time it's reduced by a factor of 10. Here we show the difference in the complexity of different implementations of the same function. So if we implement the factorial function in an iterative manner, it's of order n, because we would need to loop n times over the values. In the recursive call, we would still have the same order of n because the number of function calls is linear in n and constant effort to set up the call. So in this case, the iterative and recursive factorial implementations are of the same order of growth. Another class of algorithms or complexities is the log linear complexity, which we showed an example of it with the first bisection implementation. Other well-known and commonly used algorithms with log linear complexity is the merge sort algorithm, which we will discuss in more details in week 9. Another known complexity class is the polynomial class. One example of that is the quadratic. So the quadratic is a polynomial of order 2. However, we can have other higher order polynomial, such as, for example, of order 3 or 4. And this commonly occurs when we have several levels of nested loops or recursive function calls. Thank you.